Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to show you how to calculate with tensors by introducing a certain type of tensor calculus, which is really useful. So just as in linear algebra, there's a certain matrix algebra which allows you to calculate and work with coordinates. When you work with tensor products of vector spaces, there's this tensor calculus which becomes very useful. Okay, and I'll give two examples of this tensor calculus which illustrate the general procedure, especially in the case where we do what's called contracting tensors. Okay, so to start off with, we're going to have some finite dimensional vector spaces over our fixed field F here. Okay, there'll be V, W, and X. And so that we can put coordinates on V, W, X, we need some bases. So let's fix our bases, the VI for V, WJ for W, and XK for X. Okay, so now suppose we want to calculate inside this tensor product V tensor W. Okay, so we'll need a basis for that. And the key point is that, of course, there are lots of bases for this V and this W, but if you've given a basis for V and you've given a basis for W, then there's a natural basis for this tensor product. So that'll be the set of elementary tensors of the form VI tensor WJ. So the elementary tensors of bases from each of V and from W. Okay, and that's the basis that we're going to use. That's the induced basis from the basis for V and the basis for W. Okay, so what does it mean that that's an induced basis? So that in particular means that any element A inside this tensor product, you can write uniquely as a linear combination of these VI tensor WJ, okay? And the coefficient of that VI tensor WJ, I'll write as A upper IJ. So there's something very important in this tensor calculus which actually helps us do our calculations and really helps us keep track of a lot of information. So these actual vectors inside the vector spaces that we're looking at, they will have lower indices I and J. Okay, and what we do is for the coordinates, okay, so for these coefficients, we'll put upper indices. And the general rule is if you see an index that gets repeated, okay, that means that it has to be repeated. One half of them has to be lower and one of them has to be upper. And that's the only occurrence that you'll get. And when you see that, you sum over those double occurrence of that variable. Okay, so you sum over all I here, one occurs up here, one down here, and you also sum over all J, one up here and one down there. So that's the Einstein summation notation. Okay, so as usual, if you look at the coefficients, that can give you the coordinates. Okay, so the coordinates of this tensor A inside V tensor W is A upper IJ. And note that rather than having just one index, there are two indices, I and J. And that's because this is a very special type of basis. Okay, so basically the I index corresponds to the V, they're the VI's, that's giving you this VI here, and the J index corresponds to the vector space W here, this tensor factor here, because you have the WJ there. Okay, so that's one thing that we have, and since we've got coordinates here, we can try to calculate with that. Okay, so what types of things might we do to such a tensor? Okay, so let's have a little look at an example. Okay, and the next thing I want to do now is introduce a homomorphism, a linear map from W to X. And remember, one of the things that I showed you is that you can rewrite, in the case where this W is finite dimensional, this Hom space, okay, the space of linear maps from W to X, as a tensor product using the dual. Okay, so this is W star tensor X, okay, and these can be identified with each other naturally. Okay, now we also have a basis for this, so you can work with this vector space as well quite nicely. And this is not such an unnatural thing. You've got a Hom space, so of course this looks a lot like matrices, okay? So what is this basis? Well, you do the same thing. It's a basis for this tensor, a basis for this. Okay, you look at all those elementary tensors, and the natural one for this is you look at the dual basis. So this W upper J now, W upper J is going to be a dual basis to the W lower J. Since these are in the dual vector space, we put an upper index here like that. Okay, so W upper J tensor X lower k, these form a basis for W star, these are basis for X, so the elementary tensor products like this form a basis for this tensor product here, okay? So let's have a look at one natural construction that you can do. So remember there's functoriality for tensor products of vector spaces. V tensor W, if you have a homomorphism from W to X, we can apply phi to this second tensor factor. So identity tensor phi is going to be a linear map from V tensor W to V tensor X. So you apply the identity on V and phi on W to map you into X. Okay? So a natural question becomes, well, how do you write this out? How do you write down what this actual map is, this linear map? And the point is, well, we've got coordinates here. That's these VI tensor WJs. And of course, similarly, we've got coordinates here given by the basis VI's tensor XKs. So we should be able to say what happens on coordinates. And to do that, we need to know what phi is in terms of coordinates. Okay, so let's write down phi in terms of coordinates here. Okay, phi, well, what's the basis for this vector space of HOMs? Okay, this is W star tensor X. So the basis WJ tensor XK, W upper J tensor X lower K. And so what we'll do is that we'll write it as a linear combination of those. And using this Einstein summation notation, the coefficient of this will be written phi upper K lower J. So the upper K here matches the lower K here, so that gets summed over. And the lower J here matches the upper J now here, so they get summed over. Okay, so there's an upper and a lower index, and that's to reflect the fact that, well, one of them is a dual of starting vector space, and the other one is the original vector space here. Okay, so these phi kj's are essentially just the coordinates of this tensor. But this tensor from a dual with a vector space. Okay, so these are essentially just coordinates. And of course, if you identify this with matrices, okay, by using the basis Wj and Xk, okay, then these are the same numbers that you see in your matrix entries. So essentially, these are just matrix entries. Okay, so from that, you should be able to write down what is, for example, identity tensor phi. If you apply this map to any tensor A inside V tensor W, so maybe A is this one here, you should be able to write it out what that is in terms of the basis here, VI tensor XK. And what is that? Well, this is the formula that's given here, which tells us what it is, okay? It's going to be the sum of all ijk of A upper ij phi kj, and then that's the coefficient of VI tensor XK. Okay? So this is actually a very nice formula, okay? So what are the inputs in here? Of course, you've put in the phi and the A. The phi is equivalent to giving the data of, that's the coordinates, okay, basically. That's the coordinates of phi. This is the coordinates of A. And how do you put them together to give you the coordinates of this, this element here? Well, that's the way you put them together, okay? And this is a very, very natural formula. Let me write it in a slightly different way. So what does this map do, okay? What does this map do, okay? So you start with something with coordinates like that, A upper ij. And what does identity tensor phi do to it? Okay, you have to use the coordinates of phi to adjust that. So these are the ij coordinates, by the way. And now what we get is, of course, now since the basis is VI tensor xk, we'll write this as ik coordinates. Okay, ik coordinates. So how does that work? So to read that off, we just have to read off the corresponding term here. So you fix the I and the k, and you still need to sum over all the j. So you sum over all the j of A, what's written here, ij, phi kj. Okay? And this is how you should think of this tensor calculus. Okay? So of course you have to put the phi and the A together. And how do you put the phi and the A together? Okay, so you've got an aij and phi kj. Now this is going to be a tensor inside here. So just as A, those coordinates have upper indices, you should get upper indices here. And you see that here. There's an upper I and there's an upper K. But there's also an extra J up the top and a J down the bottom. And according to this Einstein summation notation, what you do when you're in that case is you sum over that J variable. Okay, so that's what happens here. So this is the way you should read this formula, okay, or try to remember this formula, okay. So it's fairly natural. The first time you see it, it looks a bit funny, but basically, yeah, you want to apply phi to this tensor here, the aij's. The coordinates of phi, these phi kj's, okay. So you just basically put them together in the simplest way possible. You just multiply these two, and you sum over the variable j, because at the end of the day, you just want the ik, and the j is repeated here, okay. So that's how you remember what's going on. Okay, so let's prove this, and it's quite easy to prove what's going on here. So let's just do the identity tensor phi of A. Okay, so the proof. So let's put down the proof here. So why is this true? Okay, and it's easy enough. It's just a calculation at the end of the day. Okay, so what's the left-hand side equal to? We'll work out what the left-hand side is. So it's the identity tensor phi of A. And A we can write like this. Okay, A is going to be the sum over all aij vi tensor wj. Okay, so what does it mean to do identity tensor phi? Okay, So by definition, what you do is, well, this is a linear map, so you can pull out all these sum of aij's. You apply the identity to vi and phi to wj. So this is just the sum over all ij of aij, and then you have vi tensor phi of wj. Okay, so you just apply phi of wj to this thing here, and now you need to know what phi is. So far we haven't used what phi is, the coordinates for phi. So let's work out what this is equal to. This is equal to what? So what is phi? Phi is just this sum here. The sum of phi kj, and then there's a w upper j tensor x lower k, and you're going to apply that to wj. Okay, so that's what we do here. And now we have to remember, okay, this phi is a homomorphism which maps w over to the x's. And how does it work? Well, the funny thing is that phi, now we've written it as a tensor product. So we have to think, well, when you write this out like that, okay, how do you think of it as an element of the Hom space? Okay, how do you think of it as a linear map from w to x? So let me remind you how that works. Okay, so it's easy enough. So what happens is that, well, firstly, this is a linear combination of these maps. So how does this, okay, act on this? Where does this send this to? So this is just the sum, phi kj. What you do now is that you have, this has to be some element of x. In fact, it's going to be a linear combination of these xk's. So what you do, how many xk's you have? You have w j. So I should have been careful actually when I do this, because there's a clash of notations. I've got a j here and I've got a j here, but this should be a dummy variable. So let me just fix that up right now. Okay, I'll just fix that up right now so we don't get into trouble, strife in a moment. Okay, so what we should do is make sure that this is actually an r and an s. Okay, so we'll change it, otherwise we'll run into strife and get the wrong answer. Okay, so this is rs, okay, and then the s I guess is here, and the r is here. Okay, one upper, one lower, one upper, one lower. Okay, there's an rs, there's an r, and you do ws of wj. Okay, so this is what you see here. And what is this value here? So remember, these are dual bases. So this is just delta s j, okay? So it's going to be 0 most of the time except when s equals j. So that means that you can just look at the values when s doesn't equal j, this term drops out. So the only values you need to look at when s equals j. So you replace s with j. And that gives you the final answer for what this left-hand side is equal to. It's going to be the sum of or aij. Okay, and you've still got the vi here. You've got the vi here. Tensor, we'll write down the xr. And then remember here, what did I say? S has to equal j. We've put the j here, so this s here has to be j. And then there's an r. Okay, so that's our final answer that you see here. Okay, and this is sum over all I, j, and r. Okay, I, j, and r. And if you notice, it's almost exactly the same as what you see here, except for the dummy variable that you're summing over, r here, appears instead of the k. If you replace the k here with r, there's an r, k here with r, and k here with r. This side is equal to that side there. So that's the right-hand side. Okay? And that's basically the proof of this formula. Okay? And the main thing to remember is, how does this formula work? Okay, so firstly, the proof is not that difficult. Okay, but the way it works is essentially, yes, you're going to put together two tensors. Okay, you're putting this aij here, which is this element of the tensor w. Okay, and now you're going to use functoriality. You're going to apply a homomorphism from w to x, a linear map from w to x. That's phi. That's given by another tensor. So you want to involve this tensor phi as well. And how do you put them together? So you've got the coordinates of this phi as well as phi kj, or you just multiply the aij and the phi kj and the sum over all the repeated variable j. Okay, so remember the coordinates here on the right-hand side, you will have two tensor factors, okay, and the I index corresponds to the v, the k index corresponds to the x, so they'll be indexed by I and k. And so you've got an upper I and an upper k here. and the other variable is the one that you sum over so that it disappears in the sum. It's sum over all j, and it appears once up and once lower like that. And that's the first example of a tensor calculus in this Formula 1. Our next example of tensor calculus comes from pairings. So what we want to start off with is beta is an element of V dual tensor W dual. So we introduce the dual basis for W. Let's also introduce the dual basis for V. So V upper I is going to be the dual basis to the V lower I for V. Okay? And so remember, an element beta element of V dual tensor W dual, this is naturally isomorphic to the dual of V tensor W. And that's because these V and W are finite dimensional. So we need that for this identification. And remember, linear maps from V tensor W to F, okay, by the universal property is the same as bilinear maps from V cross W to F. Okay, so this data beta, an element of V dual tensor W dual, that's just one way of thinking about a bilinear map from V cross W to F. Okay, and one of the things that we saw is that since this is bilinear, this gives us naturally a map from V to W dual. So how does that work? So suppose you fix some C inside V. Okay, so then when you look at beta tilde here, you can fix that first variable to be C, and since bilinearity means it's linear in each of these variables, that means that when you let this question mark, this blank, be any input inside W, you get a function on W which whose image is inside F, and that's a linear map. Okay, so this is how you get a map from V to W dual, and in fact this map here is also linear. Okay, so there's some natural questions that abound. Okay, so the first one is, well, how do you understand this map? This is an interesting map, and how do you write this down in such a way that you can compute with it? Is there some simple calculus that you can do? And the answer is yes. Okay, so for that you need to know the coordinates of C and the coordinates of beta. Okay, so let's look at the coordinates of beta firstly. Okay, so what's beta? Well, the way we'll think of it is it's in V dual tensor W dual. So there's a natural basis of this once you've picked your basis for V and W. Okay, so what you do is you look at the dual basis for V, so the V upper I, the dual basis for W, the W upper J. Okay, and those elementary tensors of those dual bases gives you a basis for this tensor product of dual vector spaces. Okay, so you have beta as a linear combination of them, and you write this beta out as beta lower ij of V upper I tensor W upper J. So note, as usual, the Einstein summation notation here, okay, for each repeated index, one occurs upper, one occurs lower, and it gets summed over. So this is sum over all I and j. Okay, the j also gets repeated here, one up and one lower, and it gets written like that. So of course, to think about this, remember this is a tensor product of two dual spaces. Okay, so that's the reason why firstly there are two indices, I and j, I for the V and the j for the W. Okay, and because it's not V but V dual, it's a lower I, and because it's W dual not W, it's a lower j as well inside here. Okay, so that gives you the coordinates, and that tells you basically what this beta is, and hence the beta tilde. Okay, what about C? I need to write that out, so I can write that out in terms of the basis VI. C is equal to the sum of C upper I, V lower I. And again, note there's one upper I and one lower I, so you sum over that. Okay, then what's the formula for this element of W dual? Okay, so this here is in the dual space, so you can write it as a linear combination of W upper J, that's the dual basis here. And what is that? Okay, so what you see here is this is the formula. It's the sum of C upper I beta lower I J of W upper J. Okay, so this is a nice formula. It again, you can see that there's one upper I, one lower I, one upper j, one lower j, so you sum over all ij, and at the end of the day you'll get some element of W dual. It's a linear combination of these dual basis vectors. Okay. What's happening on coordinates? Again, you can see this very similar to what we saw before. Okay, so here, I guess the coordinates, we start in V, so the coordinate here is an I, okay? And then since you're inside V, the coordinates has a C upper I. And what you want to do at the end of the day is go to something which has a lower j. So what is the coordinates here? That's the coefficient of W upper j, so there's a lower j here. And if you want to put the C i's and the beta ij's together, of course, you just multiply them together. And what do you expect? Well, you have one upper I, one lower j, so you sum over that I, and then you get remaining that j. So for each j, you'll get a different coordinate, okay? And as you run over all of them, you'll get a coordinate for this dual vector space, okay? So this looks like a very similar thing to what we did in the previous one, and that's another example of the tensor calculus of contractions. Okay, so I guess what we should do is we should see why this is true. Okay, so I guess we need to say that this element here of W dual is the same as this element here of W dual. So all you have to do, since these are both linear functions from W to F, is just show that they have the same values on a basis. So maybe WS. So suffice check what? Suffice check the following. That this beta tilde of C, comma, let's pick a basis, so that's W. So we've got S here is equal to what happens when you apply this over here to WS. So the sum of CI beta ij of Wj Ws. And actually, this is not too difficult to see what this is. Of course, this is an element, it's a scalar, it's inside F. And Wj of Ws is, of course, just delta Js. Okay, so it's going to be 0 unless j equals s when it's 1, and then you just get this term here. Okay. Okay, so let's see what this is by looking at this left-hand side. Okay, so how do you compute this left-hand side? Okay, so what is beta? Okay, so what is beta? It's given by this term here. So there's the sum of beta ij, vi tensor wj, and you're going to apply this to C. So the way this works, how do you go from beta tilde to the beta? Okay, so you just apply this to C tensor this Ws. C tensor Ws. Okay, so this is a linear combination of these linear maps, so you can pull that out. And how does this tensor, so the Vi is inside this V dual, Wj is inside this dual, how does this, what is the value of this at this tensor? Okay, so the way it works is you do Vi of C, that's going to be some scalar, because Vi is in the dual space of V, so when you substitute some element of V, you get a scalar, and then you multiply that by Wj of Ws. So this is equal to the sum over all beta ij of Vi of C, and C was just the sum of all Ci CR VR. And then, so make sure you don't repeat the I here, and then like we did before, and you multiply that by Wj of Ws. Okay, so what happens here is that we'll see that just as before, what happens, so you can pull out the sum, and you have the sum here, and then what you get is you get Vi of VR. And these are dual bases, so the only time you get something non-zero is I equals R, and if I equals R, so R equals I, you get 1, so you can forget about writing that term down. So the only term that you get that's non-zero here, when you apply Vi to this sum, okay, basically it plucks out just the coefficient of Vi, so that's C upper I. So that's C upper I, beta ij, and here you've got delta Js. Okay, so this left-hand side, do we find? Yes, it is exactly the same as this right-hand side here. Okay, and that gives you the proof of the second formula. Okay, so I hope you can see firstly the similarities in the two formulas here. And what I want to show you now is precisely why you get this type of calculus occurring. Okay, so let's have a look at the first example. In the first example, you firstly had some tensor V, tensor W, and there was some A inside here. And then what you do is you applied using functoriality a homomorphism from W to Z, to W to X rather. So basically, it came from an element of W tensor X, so that was some phi that's inside here. And you combine them together. And how do you combine them together? Well, one way to write down what that is, it turns out, is that, and this is fairly clear if you look at the actual calculation of what we do. Remember, if you have a W and a W dual, there's a contraction map. So you can map this to V tensor F tensor X. And of course, tensoring F, this is like the identity, so you can remove it. So this is maps to V tensor X. And so the image of identity tensor phi acting on this A is precisely the image of A tensor phi inside here, inside here. Okay. So what we did is we want to work out what the coordinates of the image of this inside here are. Okay. Using the coordinates of this, and the coordinates of this. Now the coordinates of this, of course, you've used the I index for this V, J index for this W. For the W star, you use the J index for this and the K index for that. And you want to end up with an I and K. So what you see in the formula here is because you're contracting this W and this W dual, what you do is you sum over the J variable. So you remove the J variable and you're only left with an I and the K. Okay, so the I kth coordinate you can get from what you get left over. Okay, so this is some sum over IJ indices. This is sum over some JK indices, and you repeat the J and you sum over the J to get you the IK index here, fixing the I and the K over here. Similarly, what happens over here? Okay, so what are you doing when you go from V to W dual? How can you write that out in a similar sort of a fashion? Okay, so in this case here, you've got some C is inside V. And then what about this beta? Where does this beta live? The beta lives in V dual tensor W dual. And what happens here, if you think about all the calculations, essentially what you've got here is, again, you just contract the V and the V dual to get F, and that's naturally isomorphic to here. F tensor W dual is naturally isomorphic to W dual. And see, what's going on here is you have an I index corresponding to the V, an I index corresponding to the V star, and a J index corresponding to the W star here, okay? So if you feed in your coordinate, which has index I here corresponding to the V, you're starting from V, you want to end up with something which has index J here. And the way you do that is, well, you've got this contraction. So the contraction means that you need to do what? You need to sum an upper I with a lower I, okay? And the J, which doesn't get summed over, tells you what the Jth coordinate. Okay, so I hope from these two examples you can see generally how the tensor calculus works. Okay, so basically you can use it whenever you're in this situation here. You're expressing some quantity that you get naturally from tensor calculus that comes from a contraction. And whenever you have a contraction of one vector space with its dual to F, okay, that corresponds to what you do. You basically perform a summation over the corresponding index for that one. I hope you enjoyed this adventure in pure mathematics.